And thank everybody for coming. So I'd like to give you a flavor of what we're doing in ACEMS when dealing with random phenomena. You can see that ACEMS is a mathematics center of excellence because of the S is an integral, you see. All right, so this will be a very non-technical talk. There will be hardly any formulas, but I hope the ideas kind of make sense. The ideas are quite mathematical, but I hope I can explain them in a clear enough way to you. So this is about randomness, and for thousands of years, people have been interested in explaining randomness, and the Greek had their own goddess, Tyche, and the ancient Egyptians had Shai. And the Romans had Fortuna, and that's actually Tyche. These, I guess you need, when something bad happens to you and something good happens to others, you need to have an explanation, you need to kind of blame someone, and that's why they had these goddesses. But sometimes random stuff happens, well, for no reason, yes? And to better understand randomness, what we often do is play games and do random experiments, because we're not born with a very good sense. Well, when we're young, we have not a very good sense of randomness. Yeah? I sometimes teach for 8-year-olds, and they have a very good intuition for numbers. But when it comes to some random experiment, kind of they don't know that if you flip 2 dice, that 7 is more likely than 5, for example. You have to find it out by random experiments. All right, so what I want to do today is to show you how you can do these random experiments on a computer. And such so-called Monte Carlo methods are now used in lots of fields of science and mathematics. All right, so here's an outline. So first I wanted to show you some randomness around us, and then how we can actually make random numbers on a computer, because there's some kind of contradiction in there, because the computer is a very deterministic device. If you tell them it's something to do something, it does it, but if you say it again, it does exactly the same thing. All right, so how can we make random numbers on a computer? And more importantly, how can we use these random numbers to our advantage? So and I want to show 3 types of applications. One is simulation, simulating random processes. Another one is estimation, like if you want to calculate some complicated quantity. And the third one is optimization. All right, so that will be the 3 pillars of, the 3 applications of Monte Carlo method. All right, so let's look at some random things around us. So because we're not very good when we're young understanding randomness, we like to play a lot of games that involve randomness, and even like now, if you play these dice are used for D&D, yeah? So 20-sided dice and 12-sided dice, etc. And say the games that do not require any skills are the games and ladders, but we kind of tend to be drawn when we're a bit older to games that require skills. Yeah, so a bit of randomness, but also a bit of skill. Yeah? All right, so backgammon kind of, I think it comes from the old Wari game that the Egyptians played, and they found dice at the graves of the mummies. I think more than 8,000 years ago. And before that, people just used probably the vertebrates of animals to predict the future. And yeah, so these goddesses, Tyche and Fortuna, they are often often associated with fate and destiny as well. Okay. So here's some more randomness. Randomness in trees. And here you see again some mixture of randomness and structure. Chaos, like traffic chaos, there's also a big random element in it. And of course the share market. And I'll come back to all of these things later on. I will avoid these bad examples here. All right. So the title was random stuff, and I didn't want to be flippant or a little bit flippant, but this is what I kind of made a connection with. So if you go to the deepest level of randomness, we are random stuff. We kind of are built out of atoms that are governed by laws which are basically random. And to paraphrase the physicist Richard Feynman, so if you want to predict, like if a light particle from A to B, if you want to kind of describe that properly, what you have to take into account is all the possible paths this particle can take. Yeah, including the one where it goes out of the door, loops around Venus, comes back, and then goes to B. All right, so at the most fundamental level, things are random, and people like Einstein didn't like that very much. He wanted wanted to explain. He thought that it would be possible to explain everything as long as you knew the boundary conditions or initial condition of your system. Okay, so Monte Carlo. So where does it come from? Well, it's a quartier area in Monaco where there are lots of casinos. And myself, I have not been to Monte Carlo, but anybody? Is anybody here? Oh yeah. But apparently, the uncle of Stanislav Ulam often visited Monte Carlo, and so these people were part of the Manhattan Project. Yeah, that was the Manhattan Project. That was the name for the project that was developing the atom bomb in the early 40s. And these people were, especially these two people, Stanislav Ulam, the physicist, and John von Neumann, the mathematician, were involved in the simulation of the fission of atoms, yeah, of uranium atoms, and it was done on an analog computer. And the code name for that project was given by Nicholas Metropolis, the Monte Carlo methods in honor of the uncle of Stanislav Ulam. Yeah. Apparently that's the story. So after the war, these people continued to do this work, this Monte Carlo method, and John von Neumann returned to the Institute of Advanced Studies at Princeton. So John von Neumann is one of the top 1, 2, 3 mathematicians of the 20th century, and he also stood at the forefront of the cradle of digital computing. All right. So when he went back to the Institute of Advanced Studies, he set his mind to the development of the digital computer, and so all the computers today, or most of the computers today, still have the architecture in them, like a CPU and memory and input-output that von Neumann suggested. Okay, so at the early 50s, people were doing Monte Carlo simulations on digital computers. And one of the earliest digital computers was, it's called MANIAC. And so what is it? Mathematical and numerical integrator and computer, I think. All right, so they were using this for integration as well. And I'll show you later on how you can integrate using Monte Carlo. All right, so at that time, around the 50s, it became clear that it's useful to have random numbers that you kind of simulate either on a computer, or maybe you simulate it on a computer and you put them in a book. 1 million random digits with 100,000 normal deviates. All right? So that's a book with just 1 million random digits. And that book is still available, and it's kind of a cult thing amongst the nerds, us nerds. You should really kind of, so you want to have one on your desk. And also, I encourage you to read the what's it called, the feedback on Amazon. Yes, I'll show you a little bit. Okay, so here's one. 1 million random digits. Ha! They only used 10 and just kept repeating them in different combinations. Don't be fooled. 1 star. This one, 4 stars. Engrossing. A very engrossing book with historical importance. It keeps you guessing until the end. Or predictable. It seems like 10% of the time I was able to predict which number was next. It was still better than Life of Pi, which, aside from being irrational, included no estimation of pi at all. Okay. Almost perfect. Such a terrific reference work. But with so many terrific random digits, it's a shame they didn't sort them to make it easier to find the one you're looking for. Okay. Pretty good, but needs some fixes for the next edition. This is a very thorough tome, and I found myself unexpectedly enjoying the numbers. However, the reason I'm giving it book 4 stars is it's very difficult to find your way back to a number you had previously enjoyed. The Rand Corporation and other publishers really need to add an index so you can quickly refer your way back to those highlights that so wonderfully brighten up the day. Okay, this one, shocked and appalled, 1 star. Those deviates were in no way normal. This is a shocking display of what our country as a whole has come to. When I was a kid, we had standard deviates and we liked it. And the next one is for people who use LaTeX, the typesetting system that mathematicians use. Yeah? Normal deviates? I don't think so, pal. Speaking as a normal deviate myself, I have to say this book is all wrong. I can't believe any real deviates were involved in researching it. What kind of weirdo has a fetish for numbers? More LaTeX, less LaTeX, guys. All right, I'll let you read this one yourself, and I'll do one more. That's very true, right? Okay, and the last one is too advanced for me. I bought this in the hope that I would be able to sit down on a rainy Sunday afternoon and look through it, and with each passing page feel a sense of achievement. However, for the life of me, I've been unable to find Waldo on any single page yet. Someone please give me some hints. All right, so I'll show you the book. One page of the book. So this is what it looks like. All right? And, yeah. All right, so what can we do with these random numbers? So the first column is just the line 1, 2, etc., so we don't need that. So what can we do with these numbers? Well, suppose that we have a group of 20 people, and we want to divide them into 2 groups. Yeah? So what we could do is give each person a coin and let them flip. And if they got heads, they go to one side. If they got tails, they go to the other side. So instead of using a coin, if you don't have a coin, you could look at this table and then just look at the numbers of the top row. And if this number is, say, from 0 to 4, then you kind of look like you simulate heads. And if this number is from 5 to 9, you simulate tail. Yeah, so if you number the person from 1 to 20, then this one goes to say group 1, group 1, group 1, group 2, group 2, group 1, group, what is it, 1, yeah, etc. So that's the way you can do it. Now, you may say that, okay, if you do it like that, then it may happen that sometimes you have 8 people in one group and 12 people in the other group. Yeah, how can we make sure that there are 10 people in each group? How can we use these numbers to do that? Can you think of a way? Well, I'll tell you the answer. So what you do is give each of the people a number, so 1, 2, 3, 4, 5. And then number 1, associated with number 1, this number here, 10097. Number 2 has this number associated with them. Number 3 has this number associated. And then you just say, okay, remember your number, and let's sort them from smallest to biggest. Yeah, and then the 10 biggest numbers go in one group, and the 10 smallest numbers go in the other group. All right, so that's how you can do like an experimental design in statistics when you have a what is it called, a control group and an experimental group. Okay. Did anybody spot Waldo? Yeah, good. All right, so now we're going to look how we generate random numbers. And here's a good quote from John von Neumann. So anyone who attempts to generate random numbers by deterministic means, of course, living in a state of sin. So the numbers in 1 million random digits were actually obtained electromechanically. But if you nowadays want to generate numbers, you use a very simple mathematical formula or algorithm. And I'll show you in a moment how kind of what the gist is of this algorithm. And I'll just show you 2 people who've done a lot of work on getting good random number generators. One is Pierre Lecuyer, and the other one is Makoto Matsumoto. And so Makoto has invented a Mersenne twister, and Pierre has invented the MRG32K38. Now, Pierre was very good at mathematics, but he failed his marketing class, where Makoto had high distinction. Okay, but actually this one is better in some sense than this one. So this one's kind of top one that is used in many programs. This one kind of passes all the known tests for randomness, where, well, in the older version, this one didn't pass all the tests, and it had to be kind of make it more and more complicated to let it pass. So it passes it now, but this one kind of can be described by half a page of code, and this one by maybe 5 pages, 4 pages, something like that. So how does it? So this is kind of the only formulas I use. So how does a basic random number generator work? And so these random number generators kind of work very similar. It's a little bit more complicated, but say the core is very similar. So what you do is you choose 3 numbers, M, A, and S0. And usually these numbers are very big, say in the billions, and maybe this is in the 100,000s. And S is a number between 0 and M. And now you want to create another number. So you start, this is called the seed number. So it's the first number in your line, your S. And now you want to make a number S1 that is formed by the previous one, S0, by multiplying with A, and then taking the remainder of this thing when you divide by m. So I'll give you an example soon. Then you output this number s, or st, divided by this last number m. And then you repeat that. Yeah? So you get s0, s1, s2, s2, etc. Okay, so here is a very simple example with m is 7, a is 3, and s0 is 1. So the rule is take your current state, multiply with a, so that's 3, and then divide by 7 and take the remainder. Yeah, so 3 divided by 7, it doesn't go any, it doesn't go in, so 3 divided by 7 has a remainder 3, so the next number is 3. And then we take 3, multiply with 3, you get 9, divide by 7, so that's 1, remainder 2, so the next number is 2. And you can see it's quite difficult to predict what the next number is going to be. So we have 2 times 3, that's 6, and the remainder, when you divide by 7, is 6. So we get a 6, and one more. 6 times 3 is 18, divide by 7, so that 14 goes in there, so we got 4 left, so that the remainder is 4. All right? So these are the s's, and then you divide by 7 to get numbers between 0 and 1. Okay, and so what we do, or kind of what was done in, say, 20 years ago, 30 years ago, is to take these numbers here. M is this number. It's a very large, well, large prime number. And A is this number. Okay, so what can we do with random numbers? These three things we can simulate, carry out random experiments. We can estimate or calculate numbers. And we can optimize. This is randomly searching. Okay, so here are some random process simulations. So think of this as a turtle. So this is kind of a random walk in 2 dimensions. So think of it as a turtle who at each step kind of turns around and chooses a random direction. Does one step forward, and then chooses another random direction, and does another step forward, and then another random direction, and another one. All right. So then this is the path that this turtle could follow. Yeah. And here we have a random tree. It looks a bit like a frangipani in winter. Yeah? And so what we do here is kind of go up and choose kind of a random angle. And these things are getting shorter according to some random mechanism. And so this is kind of a combination of some deterministic rules and some randomness built in. Yeah, if you didn't build the randomness in, it look quite artificial. By building in this randomness, it looks like a real tree. And here is a simulation of a magnetic, so it's a model for like a magnetic, say, 2-dimensional material, where each pixel represents an atom, and this atom can either be in one of 2 positions, up or down. Once you have a pixel that is black, then it's more likely to get a black pixel next to it. And once you've got a white one, it's more likely to get a white one next to it. So this is how people kind of study these ferromagnetic materials. All right, so we haven't done any simulation yet, so I want to show you some simulation. So, and I'm doing that using Python. All right. So, yeah, don't be scared by the code. But Python is a really easy to use language, and it's free. And it was invented by a mathematician / computer scientist, Guido van Rossum, when he worked at the CWE in Amsterdam. That's the Center for Mathematics and Computer Science. Okay, and Guido moved later on to Google, and he's now working at Dropbox. Anyway, so the way of generating random numbers in Python is using the rand function. So it's similar to the rand button on your calculator. In a calculator, you will have an RNB or rand button. If you push that, it will give you a number between 0 and 1. And if you call the rand function, it will give you a number between 0 and 1. And if I repeat it again, yeah, so you don't know what you're going to get. Oops. And so this number, so we can use this number between 0 and 1 to simulate how to flip a coin. Yeah, we could say, okay, if this number that I get is greater than 0.5, I got tails, and if this number is less than 0.5, I got heads. So we do that in a little program for 10 steps, so I is in range 1 to 10. If this random number is less than 0.5, I print heads, otherwise I print tails. So if I run this program, then you get heads, tail, heads, heads, tail, heads, heads, heads. And if I repeat it, you get another sequence. Yeah? And we do that, sorry, this is for 10, but if you do for 100, then you might get something like this. And you could plot either like a blue bar if you have a 1 or nothing if you have a 0. And you get such a bar plot. Yeah? It looks a bit like the one you get in the supermarket. Yeah? So this kind of represents your experiment, yeah, the outcome of your experiment. All right, now let's see how you make the turtle. So there's actually a little module in Python that's called Turtle. And this is actually quite good for kids to experiment with. So it's just, so if you do from turtle import everything, and from random import random, then you can tell the turtle where to go. So the turtle speed is 0, and it's the fastest speed. You can give the turtle a color, so and the thickness of the path. And so what is this? Do for 200 steps, you let the turtle choose a random direction, random degrees, and move forward 10 steps. And when you're done, you're done. Okay. So it goes like that. And I hope I didn't kill that one. Pardon me? Is it in the browser? Okay, yeah, sorry, yeah. It's not in this browser, yeah? It wouldn't be in here, no. All right. So I can start it again. Okay, here we go. And this tree, okay, I did also with a turtle. So let's see. You see? Okay. So let's. It's strange that I Okay, I will do a few more simulations later on. Okay, so I did this one, I did all three, right? Okay, so what about share price? So we have often such pictures for the share price. There's a real share price. And what I've got here is a random walk in one dimension. So this is a picture of the situation where you flip a coin, and with the probability a half, you take a step to the right, and with probability half, you take a step to the left. Yeah? So if you get heads, you go to the right, and if left, you go to the. If you have tails, you go to the left. And they look remarkably similar. Yeah, I'm always amused by, it's like our current day Taikis are the financial commentators, because they always have to explain certain behavior of your stock market, and usually they have contradictory reasons. So, for example, this thing here is an increase, and it would say maybe the interest rate is going to be quite low, and therefore the share price increases. And or if it goes like this, then maybe they say, okay, well, the interest rate is so low that the share price decreases because people get afraid that the economy will collapse, something like that. And then also what you often see is kind of these trend lines in these things. Yeah? But this is total nonsense as far as I am concerned, because such a picture can be easily explained by just the random walk, where with probability half you go to the left and half to the right. Yeah? So to give you an idea of how this works. Okay, so I'll do the simulation now. And you get this picture. All right, so it's a big trend going up, and then there's a big crash. Yeah. So yeah, the financial experts, or I think in the news, it's either crash or surge. I'll do another one. All right. How would you explain that one? Yes. So by doing this many times, kind of you get a bit of an idea how this works. Yeah, again, a clear trend. Okay. Oops. Okay. So we had random walks in one direction, in one dimension, in 2 dimensions. There's a turtle, and here's a random walk in 3 dimensions. And so this simulates the Brownian motion. So Robert Brown in early 1800s, he was a naturalist, and he looked under the microscope at a particle that had the same density as the fluid that it was drifting in, and he saw that this particle was moving around. And maybe he thought at first that it kind of some little animal inside, but he kind of consistently found this behavior of these particles, and this is kind of a manifestation of the first manifestation of atoms bouncing against this particle. Yeah? So sometimes So this particle can be very small, but the atoms are a lot smaller, and sometimes they bounce in one direction, sometimes they bounce in the other direction. And so this is kind of a real phenomenon. All right, so that's enough about the simulation of processes. Now I want to go to estimation. And so, for example, estimating pi. Right, so remember from high school that what is pi? Again, that's the number that you get if you take the circumference of a circle and divide by the diameter. Yeah, so you always get some 3.1 something. Or alternatively, you could look at the area of the unit disk. Yeah, so you get the area of this circle. Sorry, this disk. And you see it's less than 4 because you can put this. You bound this by a square with area 4. Yeah? All right. So so mathematicians have always been interested in pi, at least since the Greeks, early Greeks, and Archimedes already knew that pi was something like 3.14. And Leibniz found such a nice formula that pi divided by 4 is given by this. And later on, in the 20th century, Ramanujan found some amazing formulas for pi, where it's also written as a sum, but a complicated sum. And every time when you add a term, it increases the number of digits by 8. And currently there are more than 22 trillion digits now. So how can we estimate pi by Monte Carlo? Or maybe I should quickly talk about this one, Indiana Pi Bill. So there was a mathematician, or like an amateur mathematician, who thought he had squared the circle, which is basically trying to create a square that has the same area as a circle using only a ruler and a compass. And as a byproduct, and we know that we can't do that now, but as a byproduct it used that pi was 3.2 exactly. And so he had some friends in high places in Indiana, and proposed to legislate this value for pi. And the bill was passed without dissenting vote in the lower house. Okay, so, and then it went to the Senate, and it nearly passed, but it was postponed indefinitely with the help of the mathematicians who happened to be in the area, Clarence, Abiathar, Waldo. Yeah, so here I've got a picture of Waldo. Oh. Okay. So here is the basic idea of estimating pi via Monte Carlo. So what you do is look at a quarter circle. Yeah. And we know that the area of the quarter circle is pi divided by 4. Yeah? Because the total area was pi if you have the whole say disk, I should say, the quarter disk. All right. So if you would randomly sample a point in this unit square and only keep the ones that are inside the disk, then the proportion should be pi divided by 4. Okay. So that's the idea of the method. I think it's this one. That one, yeah. Okay, so I've done that here, so the code doesn't matter. But if you see that, it's so what we have here, we sample 1,000 points, and just count how many are in this unit circle, and then we multiply it by 4, we get this number 3.144. Right. And if you do it 1,000,000 times, then you get 3.140. So it's already good up to, say, these 3 numbers. But the last number, there should be a 1. Okay, so this is kind of a very small program to estimate pi. And you don't need anything very fancy. And we can do something similar for integrals. So what you do here is if you want to find, so you have some function, this is function x, maybe x1 minus x, and you want to find the area under this function. What you could do is simulate uniformly points from 0 to 1, evaluate the corresponding function value, and then take the average. So I don't have time to do that. I might do it later on. But yeah, it works very similar to what we did here. All right, so now I want to go to searching and counting. I got this haystack here because you want to search for a needle in a haystack, and sometimes if we do counting, we want to count the number of needles in a haystack. And this is a picture I sometimes do for the 8-year-olds. Counting. It's actually not so easy counting these objects. So, for example, how many paths are there from the red dot to the red dot that do not cross the same point twice? Yeah? It's not so easy. Or how many paths, random walks, are there that do not cross over? That's quite difficult. But you can use Monte Carlo using kind of a similar idea as for this pi estimation. What you can do is say, okay, suppose that this special object, say this path maybe, lies in a larger set for which you know the number, say n. Then you randomly select little n objects from this larger set, count how many are special, and then we estimate the number of special objects as capital N times little s divided by n. So if there were, say, 1 million special general objects, you select 100, and 10 of them were special, then you know that about 10% of these are special objects. Yeah, so 0.1 times n. So that's the way you can do counting with via Monte Carlo. Obviously, it's very inefficient if the number of special objects is very small compared to n, and you need more sophisticated method. All right, then we have optimization. So you've got cradle, mountain, and maybe you want to find the maximal point. Or we have some function like this, and you want to find a minimal point. So what we could do is a similar idea. So simulate points here on this line via some random mechanism. Evaluate the function values. And then see if you can simulate them in a better way. Right, you get a picture like this. So this is kind of the cross-entropy algorithm. So what you do is simulate points according to this curve, the blue curve. And so they're kind of spread out. And it gives you information about this function that you want to optimize. And the next time you get, say, this curve to simulate from. And the next time you get this one. And after 3 iterations, you kind of only simulate in this region. And after 4 iterations, you kind of simulate only in this region. So you kind of quickly zoom into the right answer. Right, and you can do that also for discrete problems. So I mentioned splitting 2 groups of 20 people into 2 groups. Yeah, so splitting groups, you can do by flipping a coin. But you can do it much more efficiently. So splitting so how do you split a group? Yeah, these people are very good at this. But how do you split a group optimally? So suppose that you have 6 people, and these people really hate each other's guts, and these people as well, and you want to have them in 2 different groups. So what you could do is for each of these people write, say, a weight that connects them, how much they like or dislike each other. And once you got that, you could give each person a coin, but not the same coin, but a different coin. There's a coin that can change, and it could be different between people. And you just let them flip a coin and do that many times. Right? So you get, say, these possible groups. And now you select the best groups amongst the ones that you simulated. And using those, you update your coins. All right, and you repeat it. So it works a bit like this thing here, but now in a discrete case. And so if you do that for 400 people instead of 20, then this is the number of possible groups that you can get. All right, and to search for the best one is quite difficult. So we start with 400 coins, all with probability 0.5. We flip a coin for each person, do this 1,000 times, take the best 100 and update the coins. Right? So this is what happens. So we start with all coins a half. And in this example, the optimal solution is such that the first 200 people go in one group and the second 200 go in the other group. So in this case, it's pretty random still. And we keep going. And now we kind of something is going on. And so it goes to the optimal solution where you have a coin which puts you in the first group for the first 200 people and in the second group for the second 100 people. All right, so here's another type of optimization problem. It's called the traveling salesman problem. So suppose that you have a traveling salesman that starts here and has to visit all these cities only once with the shortest amount of travel time. Yeah, where should the travel salesman go? Maybe this one, that one, that one, that one, that one. All right. It's not that clear, right? So what you could do is use this Monte Carlo idea of just randomly simulate paths. And some of them will actually go through the same node many times. Yeah? But you kind of update your mechanism as you go along. Yeah? So you update your random procedure by taking the best paths. And then you can repeat that and you might get a solution like this. All right, and finally, some rules that kind of Monte Carlo provides for real life, and I use them myself quite a lot. So don't always follow the herd. Sometimes set off in a random direction, yeah, because you might kind of better explore the space. Yeah, and when you do say Monte Carlo simulation with evolutionary algorithms or something like that, it's always very important to have a diverse population. Yeah, so that's also very poignant for today. Yeah, diversity is crucial. All right, and a little bit of philosophy at the end. Determinism versus free will. And we're going back to this turtle. So I said many scientists believe in determinism, that everything is kind of determined from start, that everything runs like a clock once you know the initial conditions. But what about free will? Yeah, isn't there free will? Kind of, if I raise my hand, is it because I'm destined to raise my hand, or maybe I should raise my left hand? So how do these things? Can you reconcile these two things? Well, I don't know the answer to that, but I can give you a simpler model, which kind of has both aspects. So if you think of the turtle. The turtle can go in every direction, equally likely, right? So I've made a picture here of the turtle in blue. And if you do many simulations of this turtle, most of them would kind of be like this, blue, a big mess where you started from. But if you do it long enough, maybe billions upon billions upon billions, one of the paths would look like this. Right, where you start here, and then in some certain amount of time, say, you end up here. So if we could kind of prune out these paths, then we would have interesting paths. Yeah, so maybe we can keep only the interesting paths. And so we can actually simulate these paths without having to simulate, say, the original one. So instead of kind of simulating all the original ones where you have uniform directions, we can simulate paths that start here and end up there kind of very efficiently. And this is called a Brownian bridge. Yeah, so here I have two realizations of a Brownian bridge that starts here and ends there. And both have some kind of a determinism in them, like it goes in this direction, but also have some randomness in them. So maybe that's a model for our world. Yeah. Okay, so this Brownian bridge features here on this picture, as on the pamphlet, and this picture is also in the book that I have here. And Phil mentioned his books here, and I'd also like to draw your attention to a new book that's coming soon with Slavko Botev, Thomas Time, and Slava Weissman. I apologize for the advertisement, but this is all I wanted to say, so thank you for your attention.